Hello everyone, I'm Juan Manuel Martín Doñas, researcher from Vicomtech. In this video, I'm going to present or propose audio deepfake detection system based on Wav2Vec2 for the 2022 ADD Challenge. First of all, I will introduce the motivation and scope of the ADD Challenge, including the different tracks and a brief overview of our proposed solution. Next, I will describe our system based on a Wav2Vec2 self-supervised architecture for the deepfake detection. Then, the experimental framework, including the different databases and data augmentation techniques evaluated, and the experimental results are presented and discussed. Finally, I will sum up the conclusions and future work. In the last decade, the learning-based technologies have improved in different speech processing areas, including text-to-speech synthesis and voice conversion techniques that generate high-quality voices nearly indistinguishable from real human speech. Despite the benefits of using these algorithms, we must be aware of possible malicious use of the deepfake speech with the intention of foolish humans or even automatic speaker verification systems, which is known as spoofing or presentation attacks. This threat has favored interest in reliable countermeasures in the form of audio deepfake detection systems that discriminate between bona fide and deepfake speech. An example of the research community effort in this area is the different SAVU spoof challenges from 2015 to 2021, with interest in developing anti-spoofing countermeasures. The excellent performance obtained in general clean conditions has boosted researchers' interest in more challenging scenarios where we could deploy the systems. For example, noisy environments, the use with codecs or completion algorithms, or even detect partially spoofed audio in generating utterances. To further accelerate the development of new algorithms for detecting deep synthesis and manipulated audios in challenging conditions, the 2022 Audio Deep Synthesis Detection Challenge was launched. This challenge involves 3 different tracks for the participants. Track 1 consisted of detecting audio deepfake in low-quality noise environments. Track 2, on the other hand, was about partial spoof audio. And finally, Track 3 considered an audio deepfake game between new synthesis algorithms and anti-spoofing systems to detect them. Vicomtech participated in the ADD challenge in both Track 1 and Track 2. Our proposed audio deepfake detection system is based on a Wav2Vec2 pre-trained feature extractor, which is used along a fine-tuned downstream classifier model trained for the task of discriminating bona fide and spoofed speech. Moreover, we also evaluated different adaptation and data augmentation techniques to adapt the classifier to each of the different scenarios considered. Our approach won Track 1 of the challenge while achieving 4th position in Track 2. In addition, additional experiments were performed in the SVU Spoof 2021 challenge, where our approach achieved competitive results. Now, I'm going to describe our proposed system, which includes a Wav2Vec-based feature extractor and a downstream classifier. We consider 2 different Wav2Vec2 cross-lingual language models of 300 million parameters, training in 53 and 228 languages. These models are trained using a self-supervised learning strategy with contrastive loss. The main idea is as follows. A convolutional feature encoder first computes encoder features from the raw input speech each 20 milliseconds, then feeds to a transformer network. The transformer layers use attention mechanisms to obtain contextualized speech signal representations. During training, certain code features are masked, and the objective is to predict the quantized representations among a set of distractors of the masked features from their contextualized vectors. In this work, we use Wav2Vec2 as a pre-trained model that is frozen during the system's training. The contextualized representations from the last transform layer of a pre-trained Wav2Vec2 can be enough in specific areas such as speech recognition. Still, more valuable information can be obtained at different levels for other speech processing tasks, such as deepfake detection. Therefore, we consider the representations from the different transformer layers at the input of the downstream classifier. To this end, after temporal normalization, we linearly combine these representations through trainable alpha weights parameters. After transforming them using feedforward layers, the vectors of the different time frames are passed to an attentive statistical pooling layer, which computes a single uterance representation combining weighted mean and standard deviations of the temporal features. Finally, a uterance embedding is obtained using a linear layer. A cosine distance is then computed from this embedding and a trainable wave vector representing the duration of genuine speech in the embedding space. The downstream classifier is trained to compute higher scores for genuine speech using a one-class Oman loss function. We saw good performance in anti-spoofing tags. Our proposed approach was trained and evaluated using two different speech deepfake databases. The first one is the ADD 2021 database of the challenge, which includes genuine and synthesized speech from the ASL3 speech corpus. The database consists of training and development sets of clean speech used for the different tracks. Then, the adaptation and evaluation sets are given for each track. For track 1, these sets consider real-world noises and background music in the audio. On the other hand, track 2 includes partial fake manipulation of speech using real or synthesized audio. We also carried out additional evaluations of the SAView Spoof 2021 database. In this case, we trained evaluation sets come from the ASB Spoof 2019 logical assets database. We evaluated two different tracks that consider synthesized audio in challenging environments. The logical access condition consists of a speech transmission through real telephonic systems with different codec artifacts. On the other hand, speech deepfake evaluates scenarios with processed speech with commercial audio codecs, and it also includes speech utterances from different databases. We evaluated different adaptation and data augmentation techniques to adapt the deepfake detection system to the different scenarios. First, during training, we applied low-pass finite impulse response filters to the audios in order to emulate narrowband and wideband codec artifacts. In addition, this acts as a spectral augmentation technique via frequency masking. For the ADD challenge, we include both training and adaptation sets during model fine-tuning. Finally, for track 2, we also generated new partial deepfakes using the training sets by overlapping two different audios, so the model can see more examples and better generalize. Now I will present the experimental results in terms of equal error rate metric, starting with the ones obtained in the ADD challenge. We evaluated our proposed system with different Wav2Vec feature extractors and data augmentation strategies in tracks 1 and 2. As can be observed, the 128 language model generally outperforms the 53 language one. In addition, better results were achieved when the adaptation set was included in the training, which showed that few adaptation data can help to improve the system discrimination capabilities in challenging environments. According to this, the new generated partial deepfakes in track 2 further improved the results. Finally, we also found that narrowband filtering data augmentation can reduce the equal error rate of both tracks by an additional 1%, which demonstrates that this strategy helps improve generalization for deepfake detection. To sum up, we obtained competitive results in both tracks, yielding first position in track 1. Regarding the results on ASB Spoof 21 database, we can also observe that the model with 128 languages outperforms the 53 one in both logical access and deepfake sets. Moreover, the field filtering strategy is also helpful to reduce the equal error rate of the detection system, but different filters perform better in each condition. For example, narrowband filters get better results in the logical access set, which is probably because this set includes transmitted speech over 80 kHz telephone channels, which can be simulated with these filters. On the other hand, the wideband field filters are particularly effective in deepfake set as they emulate general audio codecs. We now compare our proposed approach with previous models in the ASB Spoof 2021 database. As can be observed, previous systems based on ensemble classifiers with robust supervised models, such as like convolutional neural networks, ResNet, or ECAPA, poorly generalized on deepfake set. This fact is mainly because this database considers utterance from different speech databases as the ones used for training. Other works had previously explored the use of Wav2Vec2 for deepfake detection, but they use the contextualized representations from the last transform layer. Therefore, they yield higher errors despite using more advanced downstream models, so they require fine-tuning the word architecture for competitive performance. On the other hand, we propose using a Wav2Vec2 pre-trained feature structure with a specialized downstream model, exploiting the information from the different transformer layers. Moreover, our approach achieves competitive performance through different challenging scenarios using suitable data augmentation techniques. To conclude with the experimental results, we saw the alpha weight values used for the Wav2Vec2 transformer layers when the different tracks were evaluated. It is observed that the downstream model exploits the information from the different transformer layers for deepfake detection, with different weights distributions depending on the scenario considered. For example, it is of particular interest how for the deepfake condition, the main weights are distributed around layers 6 and 19. This finding can be interesting to analyze in future research. To conclude, I will read the final conclusions. Our approach effectively exploits the contextualized representations from the different transformer layers of a pre-trained Wav2Vec2 model. The downstream classifier can be fine-tuned using these representations and adapted through adequate data augmentation techniques. Our system shows competitive results in both ASB Spoof 2021, especially in deepfake tasks, and ADD 2021 challenges, where we are winners of track 1. As future work, we will test other self-supervised models and also additional data augmentation techniques. This is the end of my presentation. Thank you very much for your attention, and if you have any questions, you can directly contact with me in this email. Thank you.